Today we're going to take a look at controlling 9G servos using the RobotGeek system. Here I've got the FS90 and the FS90MG. The FS90 is the plastic gear version. You can see the plastic gears inside and it has a white axle here. Whereas the FS90MG has metal gears. You can see this metal top axle here. The metal gears, as well as a more powerful motor, gives the FS90MG more torque than the FS90, but they can both be controlled the same way, using PWM signals from your RobotGeek Geekduino. Both servos come with a variety of plastic horns. So these horns will fit on top of the servo. You can use a bolt that comes with the servo to bolt the horn in once you're ready. And the horns can move up to 180 degrees. Different horns can be used for different occasions and different builds. So here we've got this horn that sticks straight out. It can be handy for pointing devices. We've got this dual pointing horn that we can use if we need linkages or we need to mount something. We've also got a more standard round horn. Here's a couple of examples of ways you can use 9G servos. Here we've got a panning range sensor. So we've got a sharp IR sensor with a plate mounted to one of the horns for the servo. The servo itself can then move the range sensor. The range sensor is able to detect different objects. So instead of needing to have several range sensors at several positions, we can just have one sensor that's constantly sweeping back and forth looking for objects. This is sort of an upgrade to pan, where you've got pan and tilt. So you could mount a camera or a sensor, and then you could cover more area as you're scanning through your environment. In this gripper, the 9G servo is attached to a gear. The gears drive the fingers, and by activating the servo, you can open and close the gripper. The 9G servos have this brown, red, orange wire. The brown wire is your ground wire, the red wire is your voltage wire, and the orange wire is your signal wire. So what you might see on a RobotGeek servo as black, black, white is brown, red, orange on this servo. So here I've got my RobotGeek Geekduino and my RobotGeek sensor shield. Over here I've got a 9G servo mounted in one of our panning mounts. Underneath it I've just got a label with different degrees so you can see. And then I've modified the horn here, so I've got this pointer so we can see the different degrees we set the servo to. Like I said, we've got our orange, red, brown cable for our servo, so we're going to plug that into DIO3 with the orange moving towards signal, towards the left, brown towards the right for ground. So let's take a look at our first sketch. We're going to go to File, Sketchbook, RobotGeek Sketches, RG101, 05 Servo, Servo Degrees. So there are a couple of different ways to control servos using the Arduino IDE, and we're going to start with one of the most simplest methods. First, we're going to go ahead and upload the code to our Geekduino so we can see exactly what it does. So you might have seen the servo move a little bit. It was actually moving to the 0 position, then to 90, then to 180. So let's reset it and see it one more time. The very first thing it's going to do is move to 0 degrees. It's going to wait a couple seconds, move to 90 degrees, wait a couple more seconds, then move over to 180. Include Servo.h includes a servo library. Libraries give us access to functions and abilities that we normally wouldn't have. In just this one line of code, we're going to include a whole lot of back-end code that's going to do the heavy lifting for us, making it really easy to work with servos. We've got our constant int. Remember, constant int means that this variable is not going to change during the program's operation. That's because we've got our pin here. So our pin's always going to be 3 while we operate through the program running on the Geekduino. You can change this if you'd like, 6, 5, 6, 9, 10, 11, any of those pins that have the V in power jumpers. So first we've got this Servo1 object. Servo is the name of the type of the object, and Servo1 is the name of the object. You can almost think of this like a variable. So instead of being an integer, a character, or something else, it's a servo variable. It's going to be different than a variable because instead of storing data in it, we're going to act functions upon it. And this is going to change the data coming from the pins and then move our servo. You'll notice that we've got code in our setup and nothing in our loop. That's why this process, when we reset, just happens once and doesn't keep going forever. Our first line is servo1.attach. So this attach function is going to take the parameter of a servo pin, in our case 3, the pin that we've attached our servo onto, and attach it to servo1. So this is going to do all the setup, making sure that pin 3 is ready for a servo. Servo1.write is how we tell the servo to go to a specific position. In this case, 0 degrees. So when it first starts up, it's going to turn clockwise 0 degrees. You'll see there's another servo right here, 90 degrees straight up, and a servo right 180. That's counterclockwise to the left. We also have delays in between these rights, and that gives the servo some time to get to its next position, as well as time for us to see that the needle is stopped. So we can adjust these times if we want it to go faster, or we can change these positions if we wanted to change the way that the servo moved. So for example, let's say we wanted to start at 45 degrees, go up to 135 degrees, and then when we are done, come back to 90. Once the sketch is uploaded, you'll see us move to 45 degrees, over to 135, straight up to 90. Using servo.write is one of the more basic ways of controlling the servo, but we also have another method called write microseconds. So let's take a look back at Sketchbook, RobotGeek Sketches, RG101, Servo Microseconds. First things first, let's upload the code. Now here we see our behavior was pretty much identical to our last code where we went to 0 degrees, 90 degrees, and 180 degrees. The code, in fact, looks very similar. We've including our library, defining our pin, attaching the servo, our delays are the same. But instead of write, we've got write microseconds. And instead of 0, 90, 180, we're using 600, 1500, 2400. In a previous video, we went over PWM, pulse width modulation. And servos use a very similar method to communicate. You can send pulses to a servo. When you send a pulse that's 600 microseconds long, it moves to 0 degrees. When you send one that's 1500 microseconds long, you go to 90 degrees, and 2400 microseconds long goes to 180 degrees. Anything in between maps to degrees in between these set points. So let's take a look at these pulses. Here I've got a logic analyzer. You don't need this to complete the lesson. We're just going to use it to show you the pulses. The logic analyzer is able to read data at a very high rate, so we'll be able to see the pulses going to the servo. So I've plugged in my ground pin and my signal pin to my logic analyzer. I'm going to go ahead and reset the board and start capturing data. We've got our logic analyzer data. Let's zoom in over here towards these first points. Whenever you see this pulse high, that's 5 volts. When you see it low down here, that's 0 volts. And these pulses are moving very quickly. So you'll notice from the top of this pulse to the end, to the top of the next pulse, is always 20 milliseconds. The servos are always waiting for this 20 milliseconds. You need to have very exact timing from pulse to pulse to make sure that you're communicating with the servo properly. This is why you can't just use analog write. You have to use the servo library, which will do all the timing and make sure it's exactly right for servos. Now you'll notice here the width is 0.6 milliseconds. And 0.6 milliseconds turns out to be 600 microseconds. So that's what we were sending originally. So all of these pulses over time are telling the servo to stay at 0 degrees. So now we're going to move over until the pulses get a little bit bigger. And we'll zoom in on some of these pulses. So this is where we started going to 90 degrees. And you'll notice that our width of our on pulse is 1.5 milliseconds or 1500 microseconds. So all of these pulses were the pulses that are telling the servos to go to 90 degrees. If we go all the way to the end, the pulses will get bigger all the way to 2.402 milliseconds, which is around 2400 microseconds. So you always might have a little bit of extra delay. An extra 2 microseconds isn't a big deal. We're still getting that 180 degree. As you zoom out, it's kind of hard to tell the difference between all these different pulses, and that just shows you how exact all the timing needs to work. So why use servo write microseconds over servo.write? Well, for one thing, as we showed, knowing these numbers gives you a deeper understanding of how servo communications work. Also, being able to set these microseconds manually can be really handy for certain servos that have different bands than your standard 600 to 2400 band. Certain servos might extend out a little bit further, or they might be inward. Some servos use a 1000 to 2000 microsecond pulse. You also have a question of resolution. For servo.write, you can put in integer values between 0 and 180, so 180 different values. For servo write microseconds, you have between 600 and 2400 values. So that gives you 1800 values, or 10 times as many values as you would with servo.write. So if we have 10 times the values, that means that 600 is 0 degrees, and 610 would be 1 degree. If we were to put 605, or 0.5 degrees, we might not see a whole lot of change from 600 to 0 degrees, depending on what servo we're using and what kind of mechanical resolution it has. But even if we don't see that sort of change, it can be really useful to have this kind of resolution in our backend. It reduces rounding errors and just gives us more control over the servos and makes our robots function better. For the rest of RobotGeek 101 and for most of our RobotGeek products, we're going to use write microseconds. Now if you go to File, Sketchbook, RobotGeek Sketches, RG101, Servo, you're going to see servo write examples. These are all examples that use that 0 to 180 degree servo.write. So if you're more comfortable with that 0 to 180, you can take a look at some of these examples. The code's going to be very similar to the code that we're about to go over. But like I said, we highly recommend that you get comfortable with write microseconds, as it's going to help you a lot in the long run. So let's go on to our next sketch. We're going to go to File, Sketchbook, RobotGeek Sketches, RG101, Servo, Servo Sweep. So before, where we were just going between 3 discrete points, now we're going to hit even more points on the servo. So let's go ahead and upload. So here you see the servo sweeping back and forth between 0 and 180. We've got our servo pin just like before. We've also got constant integers defining our max pulse and our min pulse, that 2400 for 180, 600 for 0. We've also got a delay time and a servo increment. We'll talk about those in a second. We've got our servo 1 object, and we've got a normal integer variable to hold our current servo position. In our setup, we're attaching the servo like normal. We're going to put servo min into this servo position variable and then do a write microseconds with that servo position. So this is sort of a roundabout way of loading 600 into write microseconds, but it's good to get in this habit of putting this value in a variable and then using the variable to write microseconds. We'll show you why in a second. This delay just delays for a second to get to that position before all of the code starts. Here in our void loop, we've got 2 while loops. So a while loop is sort of a mini void loop, and it's going to loop everything in between it's two brackets, as long as this condition is met. So we've seen conditionals a little bit before. This is the less than operator. So this is saying that while servo position is less than servo max, run this code. So remember, servo position is going to start at 600. Servo max is 2400. So to start off with, 600 is less than 2400 and this code will run. The first line in our code, we're using the assignment operator and the addition operator. We're going to add servo position to servo increment. So that servo increment was that value of 1. So we're just going to add 1 to our servo position every time this loop runs. So the first time it runs, it goes from 600 to 601. Next loop, it'll go to 602, 603, all the way up to 2400. Once we've got this position, we will write with microseconds. Again, that's why we're sort of using the servo position variable up here, because this variable is going to change throughout this loop. And then we've got our delay time. We're just going to delay for 1 millisecond. So what this is going to do is this is going to keep looping and slowly move our needle up to 2400. Once it gets to 2400, 2400 will not be less than 2400. So this while loop is done. This second while loop is going to go from the top back to the bottom. So we've got while our servo position is greater than servo minimum. So remember, our servo position is now 2400 after this while loop, and our servo minimum is 600. So 2400 is greater than 600, and we'll run this code. Instead of adding the increment to servo position, we're going to subtract it to go back down to 600. So 2400, 2399, 2398, so on and so on. We're going to write our microseconds the same way and give it a delay. By changing the increment and the delay time, we can affect how fast the servo moves. So one of the ways we can make it all move faster is by jumping more steps. So here, where we're just jumping one step, or 0.1 degree, let's try to jump 10 steps, or 1 degree. Here you'll see the servo moving much faster, but you notice that it's not getting the full range. And the reason is because we're only delaying for 1 microsecond here, and we're not giving the servo enough time to get to its position at each interval. So we're going to have to increase our delay time too. Let's try 10. Now we can see the servo getting more or less its full reach. This is really basic interpolation. So before we were using servo write microseconds to go from 0, 90, 180. In this case, we're doing little tiny steps, whether it's that 0.1 degree we were originally doing when our increment was 1, or even now with our 10 degree jumps. And by doing interpolation, you have a lot more control over the speed and motion of the servo. So feel free to play around with this delay time and the servo increment to see the different speeds and behaviors you can get out of your sweep code. Next, let's take a look at File, Sketchbook, RobotGeek Sketches, RG101, Servo, Analog In, Servo Out. For this code, we're going to need a potentiometer, so we can use a RobotGeek knob, a joystick, or a slider. I'm going to suggest a knob because it's going to be the easiest since it's rotary and it's going to match our servo. So I'm going to go ahead and unplug the servo so that I can mount this. So I can go ahead and plug my servo back in. Then I'm going to plug in my knob to analog 0, white towards signal, black towards ground, white left, black to the right. Let's go ahead and upload our analog in servo out code. So now that we've uploaded, as we move our knob to the right, the servo moves to the right, we move the knob to the left, servo moves to the left. Let's take a look at the code. We've got our include servo.h to include the library just like normal. We're defining our pins, analog pin 0, servo pin 3, analog pin 0, servo pin 3. Our min pulse and our max pulse for our servos. We'll use that to make sure the servo doesn't go out of bounds. Here we've got our center pulse. We're not going to need it. Sometimes it's handy to copy and paste these three values directly into your code so you have all the values ready. We've got a variable for our analog sensor value, our knob value, and a variable for a servo we're going to send out to our servo. We've got our servo object, servo1. In our setup, we're going to use the attach function to attach servo pin 3 to servo1. So here in our loop, we've got the familiar analog read where we're reading from our analog pin 0. Remember that this is going to give us values from 0 when we're completely counterclockwise to 1023 when we're completely clockwise. You'll remember the map function from the PWM video. Instead of mapping to our LED, we're going to map to our servo. So we've got our analog sensor value, the value we want to map. We've got the from low and from high, 0 to 1023, the range of that analog read. And we're going to map it to servo max, to servo min. We're going to store that mapping in servo value. So 0 becomes 2400, 1023 becomes 600, and anything in between will work just the same. So 512 would become 1500. Now that might seem a little bit backwards when we're mapping 0 to the max pulse and 123 to the min pulse. But remember that when we're counterclockwise on our knob, we're at 0. Clockwise, we're at 1023. But our servo doesn't work the same way. The servo goes lowest when it's completely clockwise and highest when it's completely counterclockwise. If we were to swap these around, our behavior would be reversed. So our knob would move in the opposite direction of the servo. So let's put those back. Once we have that value, we're just going to use write microseconds to write the servo value. And then we'll have a short delay to make sure that we've got time to get to the right position. So let's go to the next example. File, Sketchbook, RobotGeek Sketches, RG101, Servo. We're going to skip continuous rotation because the 9Gs do not do continuous rotation mode. We're going to go to Detach Servo. For Detach Servo, we're going to need a RobotGeek push button plugged into digital input output 2. Let's go ahead and load up the code. We've got our pulses just like normal. We've included our library. We've got our servo pin connected to 3 and our button pin connected to 2. As you can see, as the code runs, the servo is just going to move back and forth. When I press this button, the servo is going to stop, and I can freely move the servo now. So what exactly is happening? Back in this code, I'm setting up my button pin, I'm setting up my servo, I'm writing my servo with a default value of min pulse. So here I'm running somewhat a modified version of the sweep code. Here you can see where I'm adding this servo increment, and I'm checking down here to see if I've gone past my minimum pulse or my maximum pulse. If I do go past one of those pulses, I'm multiplying the servo increment by -1, so that as it goes one way, the values go up, but then as I multiply it by -1, the values start to decrement when I add that negative value here. Down here, just like in my digital input section, I'm using digital read to check if that button goes high. When the button goes high, I'm going to use the servo1.detach function. Detach will tell the controller to stop sending signals out to the servo. Once the servo stops getting signals, it stops moving and shuts power off to the main motor. This can be really handy if you want to shut the servo down based on a sensor reading, or if you need to just shut it down for whatever reason. For our final sketch, we're going to go to Sketchbook, RobotGeek Sketches, RG101, 05 Servo, Analog In Servo Out serial. Let's go ahead and upload this sketch. While it's uploading, we'll take a look. This is very similar to our Analog In Servo Out. The main difference is that we are now going to be printing serial data to the serial monitor, just like in serial communications. So we'll do serial.begin 9600 to start our port. We've also got two mappings. So we've got our first mapping, just like before, getting our servo value in microseconds, mapping from 0 to 1023 all the way to max pulse to min pulse. We're also going to map to get this degree value. So we're going to go from 180 degrees to 0 degrees. We're just going to use this to print out on the serial monitor. So we're going to print out our raw analog sensor value, our mapped servo value, and our degree value. The code will work just like our last code worked. When we open up our serial monitor, we're going to start getting all these values out. So as I adjust this, here we can see our analog value almost all the way to 0. Our mapped value is almost to 2400, which would be 180 degrees. As we go all the way the other way, we get up just to about 1023. Our mapped value is just around 600, and we've got our 1 degree. So for example, here where we're sending a packet of 1804 microseconds, let's take another look at that logic analyzer and see if everything matches up. Change this just 1 second. Read the data. Let's zoom in. And just as we expect, 1.804 milliseconds, or 1804 microseconds. Let's come on over here. Let's try to get right around 1000. We'll read again. Just like we were expecting, we got that 1 millisecond pulse, or 1000 microseconds. That's it for the basics of controlling your 9G servo. If you are using RobotGeek servos as well, go ahead and take a look at the RobotGeek servo video. We're going to go over a lot of the same concepts, so you can use a lot of the knowledge you already have. We're also going to have a video for our continuous turn servos, and we'll talk more about continuous turn servos and using them as wheels. Stay tuned for the next RobotGeek 101 video.